on the lesson of some concept or ideas in coordination chemistry. So I have mentioned before in the previous slide on how you can calculate the coordination number based on the number of ligands that are attached to the central atom. So in this slide, I will explain on the factors that determine the coordination number of a complex. So it is always a question that how do we know how many ligands that can attach to the central atom? So the coordination number are governed by these few factors. So the first factor is the size of the central atom. Normally, the large radii of transition metals of period 5 and 6 prefer high coordination number, meaning they prefer to the central atom prefer to attach to more than 5 ligands at one time. And this high coordination number is high Cn is very common in early transition metal. Why? Because early transition metals has fewer d electron, meaning they can accept more ligand compared to the late transition metals. The second factor is the size of the ligand or the steric interaction between the ligands. If we have bulky ligands, meaning that the ligand with a very large size, they often will give you complex with low coordination number, because you know that when a ligand comes near each other, the electron tends to repel from each other, which means if your ligand is bulky and they repel each other, so they prefer to not have so many of that bulky ligand in that type of complex. So the third factor is the electronic configuration of the central metal, meaning the metal. So it is always referred to the valence electron at the outermost orbital, which is referred to the normally number of the electron in the d orbital of the transition metals. Okay, now let's take a look at complex with coordination number of 2. So coordination number of 2 usually will give you a linear species or a linear complexes, and the metals are mainly from group 6 and 7, such as copper 1, gold 1, silver 1, and mercury 2. So if you take a look at the example here, silver, for example, it is only attached to 2 types of ligand. So this is the first ligand, and then this is the second ligand. So it forms a linear complexes. But in this case, if you look at a complex here, this is actually types of polynuclear complexes, where you can see there are five gold in the molecular structure of the complexes. But if you notice, all of this gold or aurum, they tend to only form 2 coordinate covalent bonds. So this is 1, so this is 2. Okay, which means their coordination number is still 2. Okay, let's take a look at example number 3. Okay, if you look at this copper 1 here, so this copper 1 is now attached to 2 ligands. This is the first ligand. It's quite a big ligand, and then another one is another ligand. Okay, let's go to complex with coordination number equals to 4. So complex with Cn equals to 4 can show 2 types of geometry. So the first one is the tetrahedral, and the second one is the square planar geometry. And normally for tetrahedral geometry, there are 3 factors here, or 3 explanation here. And which kind of compound that can show or that can give the tetrahedral geometry. Okay, rule number 1 is tetrahedral geometry is favored if the center atom is small or the ligands are large. For example, like chloride, bromide, and iodide. So this and then the second rule, it is common for oxo anions of metal atoms on the early transition metals in higher oxidation state. Okay, if you look at the rules number 2 here, so oxo anion meaning you have 4 oxygen here. Then when you have 4 oxygen ligand, they tend to bind to the early transition metal with high oxidation state. So this high oxidation state, you can refer to the previous video on the variable of oxidation state in metal atom. Okay, so the third rule is the tetrahedral halide complexes of M2 plus ion are more preferable to the late transition metals. Okay, if you look at iron, for example, iron, cobalt, and nickel, they are all here attached to halide. So when you have halide, tetrahalide, so it is more preferable to attach to the late transition metals, like these compounds shown here. Okay, then there is another geometry which is square planar. So this square planar geometry are usually given by metal ions with D8 configuration. For example, you have nickel 2 plus, rhenium 1 plus, gold 3 plus, or PD 2 plus, or platinum 2 plus. Okay, and combination with the ligands that can form pi bond by accepting electron from the metal atom. Okay, if you look at example here, we have two types of platinum complexes. So the first platinum complexes, here these two complexes, they give a square planar geometry. However, the first one is the trans complex, and the second one is the cis complex. Okay, so this complex compound or platinum complex, they are very useful in treating cancer. Okay, between these two, cisplatin is normally used to treat cancer, but when the configuration changed to trans, it is no longer useful in treating cancer. Okay, now we have coordination number of 5. So coordination number of 5 is less common, and it can show two geometry. Either it is square pyramidal or trigonal bipyramidal. And the geometry also depend on the ligand, which if you have trigonal bipyramidal, uh, between these two, trigonal bipyramidal is a more stable geometry because the arrangement of the ligand can minimize electron repulsion. But when you have polydentate ligand, so your complex tend to give square pyramidal geometry. However, with coordination number of 5, some complexes can encounter problem in solution where the complexes can interchange between trigonal bipyramidal and square pyramidal. So this phenomenon is what we call as Berry pseudo rotation. Okay, so Berry pseudo rotation, it causes problem in the characterization if the rotation rate is faster than the detection rate in the analytical instrument. If you look at the figure here, you can see that this trigonal bipyramidal can interchange into square pyramidal and then go back to trigonal bipyramidal. So if we were to detect this ligand using NMR or nuclear magnetic resonance instrument, which you will learn in the second year. So what you are going to get is a broad signal like this. So if we analyze something and if we get a broad signal like this, meaning this signal is not very good. So in this phosphorus, so this phosphorus NMR, meaning you want to detect phosphorus. For example, this is the ligand are all phosphorus ligand. For example, you have 5 phosphorus ligand. So what happened is that you should detect um, at least 2 types of phosphorus ligand, but then you will get only one broad peak, which is not very good in terms of characterization. However, you can solve that problem if you do the measurement or you do the analysis at low temperature. So when at low temperature, the rotation rate will be slower down and you can see a very good spectrum like this, meaning you can see that in your complex just now. So in your complex, you can see um, 2 types of phosphorus atom. Okay, now let's take a look at the last coordination number, which is coordination number 6. Coordination number 6 is the most common arrangement for electronic configuration ranging from D0 to D9, and it is always found in the complexes with metal ion of 3+. Not necessarily all 3+, but most of the compound with octahedral geometry will give you 3+ oxidation state. Okay, if you look at the example here, the first one is the ferrum complex, and you can see that there are 6 water molecules attached to the ferrum ion, and the ferrum now has 3+ oxidation state because H2O is a neutral molecule, so it is 0. And now we have aluminium. So aluminium is not a transition metals, but in this case we are just going to show that it can bind to 6 fluorine ion or fluoride ion, and it is also 3+. The aluminium is also 3+. Why it is 3+? Because if you want to know the oxidation state of aluminium, and then you plus with 6 fluoride, which is equals to the number of the charge outside of the bracket, which is -3. So aluminium plus 6 minus, because F is 1 minus, equals to -3. So now aluminium is plus 3. So that's how we calculate the oxidation states. And then if you look at the cobalt here, why it is 2+ cobalt? Because ammonia is neutral and now cobalt is 2+. Okay, it's the same with these copper complexes. However, if we have coordination of by the number of 6, we can also have another geometry, which is the trigonal prismatic. So this trigonal prismatic geometry, it requires either very small sigma donor ligand or a favorable ligand-ligand interaction that can shape the complex into this geometry. And normally, this complex will be formed when you have ligands that contain sulfur atom which can form covalent bond to each other, like what drawn in the example here. Okay, so that's the end of part 3 of our learning unit 6. So I will continue the next section on part 4 and part 5. Thank you.